welcome, welcome. I'm here. I'm just getting the live started. Welcome, welcome. Please do join us. Thank you so much. Hi, Fuji. Hello. How are you doing? I'm here. Harper. Harper. Hello. What do I look like, Harper? How is everything looking? Ooh, that's amazing. Let me read that comment. 666, what does that mean? Oh gosh, how is everybody doing? Welcome to the live, I'm here. Hello. Hello, 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 hello. Good evening, good evening, good evening. Good morning, good morning. Good afternoon, good morning to Europe. Good evening to North America, South America. Good morning to Africa. Very good morning to Asia. Australia, New Zealand, Antarctica. Hello, welcome to the live. I'm here. I'm here. I'm here. Oh, hi 666. How are you? Hello, hello, hello. Ding 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 ding. Ding 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 ding. I'm here. How are you doing? It's 9 o'clock. It's 9? It's 9? Is it your bedtime, Harper? Is it 9? Is it your bedtime? It's almost my bedtime. Not really, but it feels like it. I didn't finish brushing my hair yet for the live, so excuse me. It's a little crazy up here. Hello! Hello, 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 hello. Today I'm very happy. Today is February 13, 2025. We are live! We're live, we're live, we're live, we're live, we're live, we're live. This sweater is very red. It looks correct on this iPad. As you know, I'm doing the lives on the iPad these days because there's no phone. It's extremely low technology lives at the moment, but I'm so happy you're here. You're here, you're here, you're here. You're here. Yes. Yes. Who's here? Harper. Hello. 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 Hello, Harper. Hello. Hello. Hello, Harper. Hello, Olivia. Hello, 666. Hello, Bronman. Sorry, I have to look in this direction to see your names correctly because on the iPad, the technology is such that it disappears. It disappears very easily. Amir's girlfriend, hello. PM Picks, Sportsbook Killer, hello. Great Energy, hello. Ashley North, hello. PM Picks, Sportsbook, you don't real like you are sleepy. Am I sleepy? Am I sleepy? Am I sleepy? Am I sleepy? Toaster, I'm a toaster. Hello, Toaster. Harper. Hello, Connor. Very animated. Hello, Connor. New person, 860 Phantom. What up, dog? What up? What up? What is up? The moon is up. It was a full moon yesterday. Now it's back to a waning gibbous because it goes from full to waning gibbous to, crescent and all that. New moon, full moon again, cycle. Harper! Blue Gulp! Hello! How is everybody doing? And where is everybody calling from? Where is everybody joining from? And what is your birthday month? And what is your favorite color? And what is your favorite actor? And what's your favorite movie? And what's your favorite book? And what's your favorite author? And what's your favorite subject? Tell me now! Andre, do your homework! Do your homework now! Yes! That's a great point. That's a great point. I should be doing my homework right now. Actually, right here. See, I was actually doing my homework right before this live. You're from Tennessee. Is Tennessee behind? Is Tennessee central time? You said it's 9 p.m.? That is sus. Is Tennessee in central time? I know somebody who just had a baby in Tennessee. My favorite color is green! Green? Really? Wow! My favorite color is pink. Pink! Pink! It used to be only pink, but then when I got older, I realized it's also cool to say that your favorite color is black. And I looked, I thought I looked good in black, because everyone looks good in black. So yeah. In fact, I'm wearing black right now, but I have this sweater on. Because the dress/pant dress is sleeveless and it's cold. My favorite color is blue. Oh, blue gulp. Your Sakil says, love you. So now I'm going to read all your comments. Now that I said hello to everybody. Hello, hello, hello. Hello, hello, hello. Hello, hello, hello. Hello, hello, hello. Hi, hi, hi. Hi, hi, hi. Good evening, good night, good morning, good afternoon. Australia, New Zealand, sorry. I wanted to say hi to somebody from Australia yesterday, but I was about to leave the live and they were about to enter the live. I'm so sorry I missed you. Here I am. Hello. This is posterior hello to Peter from Australia and everyone else in Australia. I want to come to Australia and I will say hello to you there as well. Okay. Can you fly? I'm flying now. Rudolph the red-nosed reindeer had a very shiny nose. I know that's not really a flying song, but it came to mind. Rudolph the red-nosed reindeer flapped his wings a lot. Do your homework. I think you're sleepy. I think you're sleepy. Can you please like the live? Nope, staying up till midnight like usual. Lol, I'm a toaster. Amir's girlfriend. Hello, Bronman. Amir's girlfriend, how are you doing? Where is Amir today? Where is that Amir? And why isn't he here to study all the astronomy today? So hyper! Andre, hello. Who else is here? The usual crowd is not here yet, Harper. As you can see. If they were here, we would hear from them. Olivia said, have you seen the movie on Disney Plus called Out of My Mind? It's about a girl who has cerebral. It's super good. There's also a book about it. I have not, but thank you for the recommendation. Thank you, Olivia. What's up? What are we talking about? We can talk about anything, but we're going to probably talk about astronomy and physics. What do you want to hear about Wade? And do you have an astronomy question? 666 says 666. Hello, quite a nice number there. Very symmetrical. Harper said, amazing, it's 9 o'clock, great energy, it is past. Said Ashley North. I think I saw your name before, but I'm happy to see it again. Ashley North. Do you play Roblox? Not yet, Blue Gulp. Tell me all about it. Not yet. Not yet. What up, Doug? Had said 860 Phantom. I'm here. Hello. 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 Hello, Harper. Hello, Blue Gulp. Hello. Wait. Hello. Oh, Capo. Rista Calistenico. Good night. Oh, Capo. Rista Calistenico. Good night. Good night. Good night. You seem extra animated today. Good night. All right, shall we talk about astronomy? What shall we talk about? Actually, let me tell you guys first about particles. I think it would be good if we talked about particles because I feel like I've talked about particles in the past and we might need a review. We might need a little bit of a review because we haven't really talked about particles recently, super duper recently. So, Relly, R-E-L-I, Relly, R-E-L-I, Relly says you. You as in, where am I from? I'm from Boston in North America. Where are you from? I'm from Boston! Freaking Andre! Hi, Dora. At this time, I'm going to be very animated because the children join at this time and their bedtime is in 6 minutes. Hi! And they think I'm 15. Like they're like a little bit older than them. Only a little. This much. K-Star, what the hell's wrong with you now? What kind of particles? Like element 115? Aw, thank you. Relly, hello. I'll be in and out, but I'll be damned. Your streams have been golden. Amazing endings. What do you mean? 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 Amazing endings. I think it's amazing throughout, isn't it? Could you please like the live? Doro, have you already left? Could you please like the live and then go? And then come back and then go and then come back and then go and then come back? So, by particles, I mean the elementary particles in the standard model. Now, not that there isn't particles and physics and more things, in general, beyond the standard model. You don't have to ask me to like the live. I want to learn English. Ooh, well, this is a pretty good live for that too. So, we can talk about beyond the standard model, but within the standard model, there are 3 main families of particles. In fact, I'm going to say them and I'm also going to type them because I want to really, really, really drill this into everybody's heads today. I want to learn English. I'm from Brazil. Wow. Welcome to Brazil. You go from depressed to borderline insane. Are you on medication? K-Star, first of all, let me just thank you for being such a regular in order to understand all my different moods on the live. I am honored. Thank you so much for watching. And could you please leave a comment in every video that you watch? I will respond to you there. Be right back. I'm going for 2 minutes. Just real quick. That's fine. Okay, so the particles that we will talk about, the 3 types of particles, these are leptons, number 1, quarks, number 2, and bosons, number 3. Hi, Fuji. Sorry, I had to move something out of the way here. Fuji is looking for his toy. Fuji's looking for his toy. 12. What is the meaning of 12? What do you mean 12? Bye-bye, pretty. Oh, thank you. Bye-bye. Bye. Oh, can you please like the live and then bye-bye? Bye-bye, Brazil. Please do like the live and then say bye-bye. Bye-bye. Bello. Bye-bye. I have, let's see how many zeros you wrote there. 1, 2, 3, lots of zeros. I have that many moods. Okay. We will be talking about particles. So that in between my moods, you can still understand what we're talking about. Did I name this live particles? I hope I did, because it is going to be about particles. Can we get 20 likes? What is Oindri B? Oindri is having a serious stream. The types of particles are follows. It's 10 people and 10 likes. 20 likes, please. They are as follows: leptons, quarks, bosons. For the people in the back. An example of a lepton is an electron, as well as a neutrino, as well as a muon, as well as a tau. Muons and taus decay into lighter particles, so you might not meet them too often. But I'm just giving you some examples of leptons. And I will type them too. For the blind. Oh, sorry, not for the blind, because the blind cannot read. For the people who cannot hear me, I will type you as well. I will type. Are as follows: electrons, muons, taus, neutrinos. Now, neutrinos do come in different flavors. I will get into that in a moment. Please hold on as I continue with the types of particles. I just told you about the lepton family, and I gave you some examples. Well, the neutrinos are 3 types: electron neutrino, muon neutrino, tau neutrino. By the end of this, you will know the types of particles, whether you like it or not, okay? Next particle type, quark. Quarks. Next type. Next particle, I almost said particle. Next particle family, in short, farticle, is quarks. Oh, God. Yes, Fuji. Mama is working. I'm so sorry. And everything is in capital letters because I'm screaming. Hi, Fuji. Mama's working, beta. Shona. 40K. What's 40K? Sorry, there's some water in my ears from the swimming. I can feel it coming out. Hi, baby. Okay, so quarks. What are quarks? What are some examples of quarks? Up quark, down quark. Which particles that we are familiar with that are not quite fundamental particles but composite particles, and those are actually made up of quarks. So they further break down into quarks. Some very common particles, in fact what we are made of is made of quarks. Such as protons and neutrinos. So quarks are the more fundamental particles which in composite form make up things like protons and neutrinos. Okay, those are quarks. Some examples I will write down now are up quark, down quark, Did you like the secret level short Doro? The next type of particle is bosons. Bosons, named after this guy with a last name called Bose, B-O-S-C. You might have heard of the Bose headphones. Same thing, B-O-S-C. There was a guy, a famous scientist from Kolkata, actually where I'm from, whose last name was Bose, B-O-S-C. Bosons are named after this person, okay? So the next type of particle, I will type all of it, is bosons. And what is an example of a boson? All around quark. What do you mean? Are you asking a question about quarks? What's the question about quarks? Thank you for the best lesson to teach is going wild on stream. Thank you for coming to this live. Could you please like it? Did you see the A Star Test 2 trailer? I think that's a question for you, Doro. Aw, you guys are all friends here. Aw. I tried to make a quark joke. Oh, that's okay. That's okay, you tried. Quark jokes are welcome. Quark jokes, boson jokes, lepton jokes. Where was I? The next type of particle that we will cover is bosons. An example, but only if you act as wild as you have been. An example of a boson is photons, light particles. Light particles are in fact bosons or photons. OMG, my cat is my Valentine tomorrow. Aww! Yay! Hearts to you and your cat. And your kitty cats. So is Baji. Baji, Fuji, and Suji are my Valentine, Thanksgiving, Christmas, everything. They come first. Everybody else comes second, third, fourth, last. Hello to Brazil again. I really love the numbers that you're sending me. I hope that they are lucky numbers. I'm not sure exactly what the meaning of these numbers are, but I am appreciating seeing them very, very much indeed. Okay, example of bosons. Bosons is photons, which are the light particles. And ladies and gents, those are the types of particles: leptons, quarks, and bosons, and we named some examples for each family. Each family quite distinct from each other. And we gave you some famous examples of each family. And these famous examples are in the chat above. If you missed them or don't know how to spell them, here is the education on that happening right here, right now, okay? Y'all need real Valentines. Saturday night is my Valentine's. Some of us got work schedules. Who said we need real Valentines? Why do you think that we don't have real Valentines? Who and why? And why would we need a Valentine? What is a Valentine? I am eating pizza. I'll mention Warhammer for you. Oh, that was to wait. Got it. Fuji is so cute, yes. He is. Thank you. Thank you, universe. I'm working too, gonna have to bring something home. Okay. All right. So we have talked about stars and the Big Bang nucleosynthesis. In fact, remember how we talked about the Big Bang nucleosynthesis mainly involved the cosmic plasma. When we talked about that, remember it was mainly photons, electrons, and positrons in this hot, dense, energetic, not cooled down enough cosmic plasma where things were mostly in equilibrium. And we also mentioned about neutrinos having a bit of a breakup with that cosmic plasma because the expansion rate was actually a little bit faster than the interaction of the neutrinos with the cosmic plasma. And then we also mentioned baryons, because remember in cosmology, mostly all of the ordinary matter kind of fall under this category called baryons. Because depending on which field of physics you're in, you might call things with different naming. So the naming I just mentioned, the leptons, quarks, and bosons, that's a very that's a very particle physics standard model particle physics way of calling the different particle families. If you're thinking cosmology and you just want to club together all of the ordinary matter and just call pretty much all the protons and neutrons by some clubbed name, some group name, then people say baryons. So we mentioned how in the Big Bang nucleosynthesis, the baryons did have a role to play, and as things started to cool down, we started to make a little bit of hydrogen. In fact, that is what the Big Bang made. Pretty much as far as matter goes, because back then was a very radiation-dominated universe. We also talked about the evolution of the universe in our cosmology lives, which I encourage you to find and follow and listen to or watch as you please under the live tab, because we actually cover a lot of the early universe and evolution of the universe and kind of what happens in what era of the universe in those cosmology lives, because we have spent a lot of time talking about astronomy, which is sort of more specific events, phenomena, and objects in the sky, including galactic events and galactic objects, as well as extragalactic objects. But then cosmology is really the more larger scale field that goes into the details of the universe and how to think about the universe, and also the evolution of the universe from the start to where we are now. And we talked about how the universe has changed, just like we change, just like human beings change over time. And we think of things in terms of maybe decades. It's maybe of value to think about our astronomy, galaxy, the cosmology universe in terms of giga years. So thinking about which things sort of happened in which billionth year. Given that the universe is only about 14 billion years old, you might want to think about, okay, in this giga year, this happened, and in the beginning, sort of first giga year, what might have happened. And in fact, we have something very exciting from the first several 100,000 years of the universe, which is really very early, which is the cosmic microwave background photons, of course. So basically, I mentioned about the giga years to give you some idea for the timelines, because we shouldn't expect the universe to change on the timeline of us human beings, right? In fact, another little reference for you here is that Earth and our solar system is around 4 giga years, right? It's around a little bit over 4 billion years old. And the sun is a relatively new star. It has, the sun and our planets were formed out of a nebula, a gas cloud, condensating at some point to make our solar system. And ever since, the sun, of course, has gone around the galactic center. So just like we orbit the sun, the Earth, I'll start with the moon. The moon orbits Earth, the Earth orbits the sun, and our sun orbits our galactic center. We have a supermassive black hole at the galactic center called Sagittarius A star. We have also mentioned quite a bit about this black hole and the galactic center. So the sun, you might wonder, in its lifetime of just a little bit more than a few giga years, how many times has it completed revolutions around our galactic center? And that number is only about 20 times. So the sun is not quite a teenager anymore in terms of our galaxy, because 19 would have been a teenager. It's 20, so it's a young adult in terms of stars. So quite young, quite new. And of course, there was no sun, as an example, when the universe was getting started. There were no stars when the universe was getting started. The first stars are what we call very metal poor. Yes, sun's old enough to party. Yes, the sun is not old enough to drink yet, in the US at least. Maybe the sun can drink in the Caribbean islands, US Virgin Islands, where you can drink at 18. It's a territory of the United States. So with different laws. So the sun is quite new, for example, in terms of the universe. The sun, another thing to note about the sun is that it's not considered a metal poor star, because it's a newer star and it was made out of that pretty metal rich. You can verify this and get more reference for this yourself. But when you are made out of a pretty metal rich gas cloud nebula thing, then chances are you're gonna have quite a few metals in you, like our sun does, and even we do on Earth, right? We have metals like gold on Earth, right? Where from do you think that comes? We all come from some nice metal rich enough thing that cooled down, condensated at various distances. Well, first of all, it made the sun, but also it made the planets sort of in the same plane as the sun, actually. Very, very interesting. Most of the mass of it went to the sun, and most of the angular momentum of this nebula that we come from, went to the planets. So, but we have these amazing things on our planets, including our own planet, and that is very nice. That is because we are relatively new, and enough time and enough sort of things happened where we got these metals, because really all of the elements above hydrogen, mostly, I would say definitely above helium, but even helium is made in stars. So when the universe was getting started, long story short, well, I don't know if this story can be that short, but when the universe got started, there were no stars, is what I was trying to say. So it was not very metal rich. There was indeed very few baryons, where baryons are, of course, ordinary matter, such as what we are made of, you and I, protons and neutrons, the elements. Because remember, the elements, what do we mean by the elements? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, those are the elements, right? The entire periodic table is made in stars if it's an element above hydrogen, because the Big Bang, when the universe got started, made very few baryons, even hydrogen, very few, like not so much where, we got a ton of helium, for example, because later on, you get helium also from hydrogen. So we made we made some hydrogen in the Big Bang, and we made a little bit of helium, and very trace amounts, as in, if I forgot to mention it to you, it would be fine, trace amounts of lithium. So the Big Bang is responsible for hydrogen mainly. Thank God it made hydrogen, because that would be really hard. Then there would be nothing, because hydrogen, and making hydrogen is not so difficult either, because it's just a proton. When we were back then in the beginning of the universe, or close to the beginning of the universe, things were not really neutral atoms yet. So when I say hydrogen, what I really mean is protons. There were protons, so there were baryons, and then we made some helium as well, and then we had very tiny amounts of lithium. And then once things cooled down more later on, and we started to form structures and stars and galaxies, and the first stars. So the first stars, meaning the first population of stars, are very metal poor, because they are the first stars. Like they did not come from a metal rich background. They made more elements in their environment, and then when they died, they enriched their interstellar medium, the medium around them, with the metals that they made. And then we had more elements, and then that made more stars. And then when those stars died, again, that enriched the interstellar medium more. And then that made more metal-rich clouds again, gas clouds. And then from there, something like our sun or its predecessor was made. Okay, so just like elements hide from the solar system. What do you mean? Hi, Willie. I never see my son, S-O-N. The periodic table, I mean, if you don't need it, you could use it to wipe your backside, because I could just tell you the periodic table right here, right now. Heavier and heavier elements, exactly. So, hi Alex Knit, A-L-X-N-L-T. Hello Harper, hello Willie, hello Alex Knit. So this is how we get, as somebody said, heavier and heavier elements. So even in our own galaxy, right? Even in our own galaxy, in the halo of our galaxy, because we've mentioned how our galaxy itself is a quite an interesting, substantial, big, bright, ton of luminosity and spiral. Of course, it falls under the spiral because that's just based on shape. So galaxies are classified based on their morphology as spirals, ellipticals, and irregulars, based on literally their shape. Irregular shape is some galaxy that is yet to form a nice shape because it's probably made out of merging with another galaxy. We mentioned some examples of that if you're following my clips and lives and things like that. And then elliptical galaxies are galaxies in the shape of an ellipse. Ellipses can be of different types, of course, with different ellipticities. And then spirals are like our own galaxy. And we talked about our galaxy is quite a substantial galaxy. Not every galaxy is like our galaxy. Our galaxy has a lot of stuff. It has a lot of stars. It has a supermassive black hole. And its luminosity comes in a variety of wavelengths. So for example, we've talked about our quite bright galactic center where you get a lot of radiation in radio waves, in X-rays, and because we have a supermassive black hole, we're just making things accrete into it, as in it doesn't just eat up material from its surroundings in a straightforward way where the material just shoots straight down into it and then is lost in the black hole forever, but it makes things accelerate and fall into it after doing a dance where that dance makes us be able to see it in a very bright way. The accretion of material and all the acceleration of the material, and this is what's emitting the synchrotron radiation and Compton and all these different processes of radiation from the material that's falling into the black hole. So that material falling into the black hole makes it very bright. But also, we have a ton of stars. We have a ton of stars. Not all the same stars. So I'm going to mention, I was talking to you about metal poor stars, or the first stars, and how stars were not always so metal rich. That's where I got started talking about our own galaxy, because even our own galaxy gives you a glimpse of that, gives you an idea for the diversity of stars that there really is in the universe. So, for example, let me finish the thought of where our galaxy has a ton of luminosity, of course, coming from the galactic center. Some galaxies that we talked about, remember, in a different live called active galaxies, those galaxies, the most brightness from those galaxies, the majority of the luminosity of those galaxies actually come from their galactic center. They have an active galactic nucleus. So those galaxies, that active galactic nucleus is basically competing with the luminosity of everything else put together, right? So when that happens, we call those active galaxies or active galactic nuclei. But when you have a galaxy like our own, which is a spiral normal galaxy, where we have a ton of radiation from the galactic center, but we also have a ton of luminosity coming from all the various stars we have a lot of stars. We have 200 billion stars in our galaxy, if I remember correctly. You can always double check that number. Then we call it just a normal spiral galaxy. We don't call it an active galactic nucleus. And the nice thing is, or the interesting thing is, that even in our own galaxy, we have both metal poor stars as well as metal rich stars. We actually looked at a picture of our galaxy and we saw there were all these different spiral arms, and some parts had the metal poor stars and some parts had the metal rich stars, actually. And so where are the metal poor stars in our own galaxy? In the halo. So our galaxy has three parts. We have the disk, the bulge, and the halo. The bulge has to do with the galactic center. And so I just spent a little bit of time talking about the galactic center already, but the halo is just like this big sphere that's all around our galaxy and goes way far. And that's where you'll find a ton of the older stars or the metal poor stars. So even in our own galaxy, there's all these different diversities, there's all these different varieties of stars and whatnot. And that reminds you that things have evolved a lot. Where we are today, that is not how things always were in the universe. The universe was very radiation dominated in the beginning, then it became more matter dominated, and now it is dark energy dominated. We know that right now the biggest cosmic ingredient, the most abundant, I don't want to say abundant, actually, the biggest fraction of the energy density comes from dark energy, followed by dark matter, followed by ordinary matter. I didn't want to say abundant because sometimes I ask the quiz question on this live, what is the most abundant element in the universe? And by that I mean, what is the most abundant element out of ordinary matter periodic table? And the answer to that is hydrogen. But what I was just now talking about is the overall cosmic ingredients, everything in the universe. We talked about that as well. The cosmic inventory is like 5 things: photons, baryons, neutrinos, dark matter, and dark energy. Hydrogen is never the answer. Hydrogen is the answer if I asked what is the most abundant element in the universe. So, yes, we did talk about quasi-stars or quasars. Do you want to hear about that? We talked about quasars under active galaxies. Look at this. So, as I was mentioning, did you know that galaxies are of different types? We classified galaxies as the spirals, the ellipticals, and the irregular galaxies based on their shape. But what if I were interested in galaxy classification with regard to the activity in those galaxies? So since somebody asked about quasi-stars or quasars, that's exactly how you say it. So very good job, ALXNLT. And please do like the live while you're here, especially if you're joining just now. So if I were to be interested in figuring out, oh, it's not you, okay. If I were to be interested in figuring out the activity in galaxies, and in fact, I just mentioned how active galaxies are the ones that, let me rotate, let me put this over here. Can you guys hear me okay, by the way? Everybody here can hear me fine? Everything good? Thank you for liking the live. Thank you for liking the live. So, okay. Whoops. Okay. So if we were to be interested in sort of the activity of the galaxies, and in fact, it's really to do, everything in astronomy is really to do with luminosity and what we're measuring. So even the discovery of quasars had to do with what we measured, what we saw, you know, and they weren't really, they weren't sure what they were looking at because, so you asked, do you know about quasi-stars, which I thought that was a very interesting question because you said it exactly correctly. The way we saw these quasars are basically, we thought they were stars. They're galaxies that looked like they were stars. That's how much of their luminosity was concentrated in the center of them, you know, the active galactic nucleus business that I was talking about. So our galaxy also has a supermassive black hole that is accreting material into it, but we don't call our galaxy an active galaxy or an active galactic nucleus galaxy. Why? Because most of the luminosity of our galaxy don't come from the supermassive black hole galactic center. It comes from the stars in our galaxy, like a normal galaxy. But there are galaxies that are called active galaxies where most of the luminosity is dominated by their galactic center, which is generally an active galactic center or an active galactic nucleus is what the word is. So there are 3 types of active galaxy. There are 3 types of active galaxies, if I can speak. These are Seyfert galaxies, Seyfert. I will type them. Active, since you asked, I'm going to cover this now. Active galaxy types. Seyfert galaxies. Seyfert galaxies, quasars, or quasi-stars. Oops, I can't type. Are you still here? The person who asked the question? Quasars or quasi-stars, so galaxies that we thought were maybe stars, and then radio galaxies, okay? In fact, I'm about to tell you something very interesting about quasars. We actually, hi, I have OCD. Okay. We actually thought when we saw the first quasars, when we first discovered quasars, we thought we actually saw the more, what's the word? The less dominant type of quasar, the less dominant population of quasars. And that's because of how interesting or how different they were. Like, you know how, unless you see something kind of weird or different or it shocks you, you might not take note of it. So basically the discovery of quasars, it was just like so weird. It was like, what is this? It's like, this is so star-like, but maybe it's not a star. Is it a galaxy? What kind of galaxy would look like that? But because of that, we also discovered, so it's good, we discovered a new type of galaxy, quasars, but also, funnily, we discovered the type of quasar that is actually less common first. Dora is busy, so he can't get rid of these trolls. Hanging with Acha, someone tonight, not even answering me, but I'm here. Okay. Thank you. Thank you, Grimmy. One second, sorry. Oh wow, Dora is here. Oh, thank you. Let me stop bothering me. Okay, so sorry, let me get back on track. Let me clip this. I was talking about the active galaxies and how somebody asked about quasi-stars or quasars, which is, I'm very excited about that question. I'm going to answer it in detail. We just talked about the different types of active galaxies, Seyfert galaxies, quasars, and radio galaxies. And I mentioned how it was funny how we discovered quasars because we first found the less dominant type of quasar. But let's now read about quasars in detail, okay? So let's do that. Okay. Now, Seth. Happy Valentine's Day. Thank you. Can you please like the live? Thank you so much. Have a great Valentine's Day tomorrow / today, if it's already Valentine's Day for you today. Thank you. Okay. Okay, so sorry. Now we will talk about quasars. So radio telescopes first surveyed the sky in the mid 20th century. So since somebody asked about quasars and I gave you a little bit of an introduction already, now let me give you the super duper formal introduction from this book called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. Thank you so much to the authors as usual. They were my professors and we are most indebted to their awesome book. Radio telescopes first surveyed the sky in the mid 20th century. These first surveys showed that the optical counterparts of most radio sources were galaxies. The radio galaxies discussed in the next section that we also mentioned as a category of active galaxies. However, some radio sources did not have obvious counterparts. Ambiguity arose because of the poor angular resolution of single dish radio telescopes. Once better radio positions were obtained, it was found that the radio sources were associated with blue star-like objects. So that's where we get quasi-stars, because we thought that they were actually stars, but they were not. Turns out that they were galaxies, but we'll find out. This was unusual. Stars are not generally strong radio sources. So this is where we scratched our head. We're like, these are radio sources. And so this is where we basically found the radio loud, what we call very bright in radio, types of quasars first. We thought that they were stars because they were so star-like or point-like. Thank you for liking the live. Can we get 20 likes? But they turned out to be some very interesting galaxies, actually. So it seemed clear that they were not stars. So their star-like appearance led to the name quasi-stellar radio source, which was later contracted to quasar. So it's really, we call them quasi-stellar, quasi-star, quasi-stellar, later on quasar. So we will look at an example of a quasar here in a bit, 3C273. You can even Google this yourself, and we will look at the picture here, 3C273, one of the first quasars to be identified. Note how the quasar, so we will look at it, but when we look at galaxies, they are more of an extended, when we really zoom in on galaxies, they look like a more extended body. Now that body can have a spiral shape, an elliptical shape, an irregular shape. Even the large Magellanic Cloud and the small Magellanic Clouds, they are still galaxies. They're irregular shaped, more extended bright objects. So they're not point-like or star-like. They're still galaxies. But in this case, it was weird because they strongly resembled stars, but they were also very bright in radio. So note how the quasars more strongly resembles the stars in the field of view than the two fuzzy extended galaxies at the left of the figure. So we will look at this in just a bit. When the spectra of these quasi-stellar radio sources were obtained, things became more unusual still. The spectra contained strong, broad emission lines that did not correspond to any known element. The breakthrough to understanding came in 1963 when Martin Schmidt had a eureka moment while looking at the spectrum of 3C273. He realized that the emission lines in the spectrum were Balmer lines with a redshift Z of 0.158. Okay, no one had been expecting such a high redshift. Like people thought, these were like stars or something, or weird stars, you know. It corresponds to a radial velocity of 47,000 kilometers per second and a distance of 680 megaparsecs, so quite a bit far from us. The large distance was itself impressive at the time, but hardly unprecedented. Clusters of galaxies at redshifts as large as z equal to 0.2 were already known. So we knew clusters of galaxies that were at higher redshifts, like a redshift of around 0.2. But the problem was that this thing was kind of weird. It was star-like, it was at this high redshift, it was radio loud, and we were just kind of, you know, confused by all of this. However, what was extraordinary was the luminosity implied by the large distance. So it even more makes it so that it's such a large distance away, which means that this thing is really luminous. It's quite extraordinary. It's not a normal kind of luminosity. A quasar a quasar is an AGN that has a very high luminosity. So again, AGN is active galactic nucleus. Let me put that in the chat. Active galactic nucleus. Yes, I do some singing sometimes. I can do that today as well, later on, but I gotta answer the question about quasars first. We first do the serious stuff. So what was extraordinary? So again, I put that in the chat, active galactic nucleus, or AGN. What was extraordinary was the luminosity implied by the large distance. A quasar is an AGN that has a very high luminosity, where the luminosity is now 10 to the 38 watts or so. The most luminous known quasars have around luminosity of 10 to the 41 watts, or which is around 3 times 10 to the 14 luminosities of the sun. So 3 times 10 to the 14, that's quite a bit of solar luminosity. The reason why they look quasi-stellar, so quasi-star-like, is that quasars are much more luminous than the sum of all the stars in the galaxies that contain them. So it's like the active galactic nucleus itself is giving off so much luminosity that it's like a really bright point-like thing at a very large distance, making it seem like a star more than a galaxy, which we would consider to be a more extended body of brightness, right? So the quasar, the reason why they look quasi-stellar is that quasars are much more luminous than the sum of all the stars in the galaxies that contain them. Thus the quasars usually appear like unresolved points of light, just like stars. It's initially difficult to believe that the highest and lowest luminosity AGNs represent the same phenomenon. Indeed, as we'll describe, the energy requirements needed to explain quasars were so radical in the 1960s that a 20-year controversy over the nature of quasars ensued. Are they high luminosity versions of Seyfert galaxies at the large distances implied by their redshifts, or are they low luminosity nearby objects of some sort with their large redshifts due to some other effect than the expansion of the universe? For most astronomers, the matter was settled definitively in favor of the former hypothesis in the 1980s, with the detection of stellar absorption features in the faint fuzz surrounding quasars. The remarkable properties of quasars soon led to more efficient ways of discovering them. For example, quasars are very blue compared to stars. So you know, they looked like stars, but there were some odd properties that sort of gave them away as maybe these are something different. You know what I mean? Like, it's almost like thing after thing being discovered about them is making them more and more confusing and hard to resolve, quite literally, as stars. Okay. I'll keep going. The remarkable properties of quasars soon led to more efficient ways of discovering them. So because these things are so different than stars as well as galaxies, because they were too radio loud to be stars, and they were too point-like and luminosities too in the nucleus of them to be normal galaxies. So it's like, what are these is the question here, you know? So the remarkable properties of quasars soon led to more efficient ways of discovering them. Once you know what you're looking for, though, just like Sherlock Holmes, it's easier, you know? Like, once you start looking for these crazy things, maybe you'll find more, and maybe then you start to characterize them and you figure out, oh, so this is what we're looking for. Hi, Suji Mama. She's like right below me. She comes around and brushes against me to let me know that she's here. She's very subtle, kind of like quasars. But basically, once you know that there is a quasar, once you know what you're kind of looking for in terms of the properties, even though they're weird and you're unable to easily categorize them as either a star or a galaxy, but you can say, oh no, this is what we are looking for. It's this crazy thing that is, you know, kind of like really far away, kind of really point-like, lots of luminosity in the center. We thought it was a star, but maybe not. Then you can maybe find more. So for example, quasars are very blue compared to stars. So searches for objects with ultraviolet excess, you know, you can just say, look for objects with ultraviolet excess relative to starlight, of course, proved to be especially effective. So when you do that, you find more and more of this crazy object. Moreover, it quickly became apparent that there was an even larger population of objects that had the optical properties of quasars but were weak or even undetectable emitters at radio wavelengths. So as I was saying, we found those radio loud quasars first, but those are actually the more rare type of quasars. But because of the sort of, because of how weird they were, they stood out, and we delved into it deeper, and we tried to find more of these things with ultraviolet excess, and we found more. But these were actually, what we found more of were actually the more radio quiet ones, the more where we see them in optical or other wavelengths. So these radio quiet sources became known as quasi-stellar objects. Also, you know, we're still on quasars, or simply QSOs. The original radio loud quasars actually make up only 5% of the total population of quasars. So this is what I was saying when I got started with the topic, which is that sometimes you find something really crazy and it's actually the more rare type of that thing, but the ridiculousness of it, or the interesting properties of it, gives it away, you know, and helps you to discover it. But don't expect to keep discovering only that kind of that thing. What we found more of is actually the more radio quiet quasars. Isn't that interesting? Intensive searches for quasars turned up yet another variant of the Aegean theme, objects that are known as BL-lac objects. Unlike Seyfert galaxies, which are named after their discoverer, BL-lac objects are named after their archetype, BL-Lacarte. The name BL-Lacarte is the type of name, 2 letters plus the Latin genitive form of the constellation name that is given to a variable star. So we also talked about pulsating variable stars the other day. So hopefully that live can help you with some more examples of variable stars. But in fact, BL-Lacarte was originally thought to be a variable star within our own galaxy. However, deep exposures revealed that BL-Lacarte is not a star but a distant elliptical galaxy. Its redshift is 0.07, puts it at a distance of around 300 megaparsecs, so closer than that first quasar. The reason why BL-Lacarte was originally mistaken for a star was that its unresolved nucleus is brighter than the diffuse fuzz of starlight surrounding it. So it's like really, really bright center and diffuse fuzz. The nuclei of BL-Lac objects are rapidly variable and have a non-thermal spectrum, but do not show any emission lines. This makes it difficult to determine the distance to a BL-Lac object unless you can manage to detect the absorption lines in the fuzz of starlight. Doing so is very difficult for many BL-lac objects since their nuclei are so extraordinarily luminous compared to their stars. It also makes it difficult to determine their morphology. It's conjectured that all BL-lac objects are ellipticals, but no one is totally sure. Could you please like the live? The flux from a BL-lac object can change significantly from one night to the next. Again, that's what is true of the variable stars, right? Their flux changes a lot, constantly. So look at the live where we talked about the variable stars as well. The flux from a BL-lac object can change significantly from one night to the next. This indicates that the bulk of the luminosity comes from a region less than 1 light day, 200 astronomical units across. So basically, if the flux is changing so much over the course of one night to the next, that means that a lot of the luminosity, again, is coming from a very point-like or very concentrated region, which could be, in this case, it is 1 light day across, which is around 200 astronomical units across. So Seyfert galaxies were first noticed because someone looked at images of spiral galaxies and said, wow, those nuclei are really bright. BL-lac objects were first noticed because someone looked at the radio emission from BL-Lacertae and said, wow, that's way too much radio emission for BL-Lacertae to be a star. So this is kind of how the active galaxies were discovered, and that was a little bit of a tidbit from active galaxies, particularly on quasi stars, as somebody asked, or quasars. Hopefully that was helpful. It's from this book called Foundations of Astrophysics by Barbara Ryden and Bradley and Peterson. We talked about normal galaxies as well quite a bit, spirals, ellipticals, irregular galaxies based simply on their shapes or morphology. Now we also talked about active galaxies, where the main thing is that the galactic center of these active galaxies basically are very active, as in they are the producer of the maximum luminosity of that galaxy, and they outshine the rest of the galaxy and the rest of the stars in the galaxy by lot. And when we see them, first of all, we thought some of these could be stars. They were very star-like, and we were like, oh, what are these things? They seem to be too radio loud, because we found the radio loud quasars first. They seem to be too radio loud to be stars, but they also are very far away, and they also, you know, the luminosity is still concentrated in the center. So that's where we are like, oh, maybe these are, you know, active galactic nuclei, and we start looking, and then they had the ultraviolet X's as well. So then we start looking for more of them. We found the radio quiet ones, which happened to be most of them, and overall they belong to that active galaxies category of galaxies, which is the active galactic nucleus category, where there is a very high luminosity center doing all of the things, and pretty much a very dim blur of stars around that center, because it's not really a fully developed, substantial, normal galaxy where the stars would have similar or more luminosity contribution to the galaxy, like our galaxy does. So that is the little spiel on active galaxies. Hopefully that was helpful. Let me know what you thought of that. Yay, can we get 20 likes, please? 2 more likes. Could we get 20 likes? Yeah, because I talked about science. Somebody asked about quasi-stellars or quasi-stars or quasars, so I did the full spiel on quasars. And it became a little quiet. Radio quiet. Yeah. Somehow there were more trolls today. I don't know why they come more to the sciencey lives, because it's disruptive, but when I'm doing the crazy lives, somehow there's no trolls then. Weird. I want the trolls to be more disruptive at the crazy lives, because the crazy lives don't require any concentration. How's your night, Doro? Oh my goodness. Are you done already? I mean, that was fast. Oh. Hi, Baji. Baji's over here. Reese! Hello, Reese. Reese and Doron, you're both here now. My excellent mods. Fell asleep. It's me, had such a strange dream, lived in America. You dreamed of America. Of me. What was that song again? I found a girl. You dreamed of America. I see Grimmy says I had a eating food. America rules. Come live in the US. Now I will sing a song for everybody to finish up this live. And I want 20 likes. Right the frick now. Let's go. I will sing perfect for you now. Perfect lyrics. Ed Sheeran. Because Reese is here. His favorite song, favorite singer is Ed Sheeran. I can't give more likes. Well, I talked a lot about active galaxies again, which is good because I feel like I covered them in a little bit of a rush earlier. And before that, I was showing up with a lot of energy. And some people said that I was on medications or maybe off medications. I found a love for me in America. Darling, just dive right in and follow my lead. Isn't Ed Sheeran British? You must love Ed Sheeran. You love him. You're lying. Darling, just dive right in and follow my lead. Well, I found a girl, beautiful and sweet. Oh, you should sing this for your friend. In fact, that'll wake her up. I never knew you were the someone waiting for me. 'Cause we were just kids when we fell in love, not knowing what it was. I will not give you up this time. Darling, just kiss me slow. Your heart is all I own. And in your eyes, you're holding mine. Harper, do you like this song? You're the only supportive one of my singing. Do you like this song, Harper? My French ex was in my dream. Good God. Good God, your dreams are quite active, like galaxies, active galaxies. Harper, do you like my singing? Someone. Oh. I sing, okay. I need affirmations while I'm singing. Baby, I am dancing in the dark with you between my arms. Keep on doing it. Barefoot on the grass while listening to our favorite songs. When you said you looked a mess, I whispered underneath my breath. You heard it, darling, you look perfect tonight. Da-da-da-dum. And with that, I will be leaving you guys. Yes, please send her my stream. Just for the Korean lady, I will sing a little bit more. I found a love for me. Darling, just dive right in and follow my lead. Okay, you know what? I'm done. Good night, guys. I'll see you tomorrow. You're speechless. Are you really speechless? Oh my gosh. I made friends with the... I'm speechless. Harper, thank you, honey. Thank you. You know, all my singing is actually just for you, Harper. Thank you so much. See you tomorrow night. Have a great sleep. Good night. Sleep tight. You took my breath away. Aw, really? Which part? I found a woman. Beautiful and sweet. I actually kind of don't like these words. Follow my lead. Harper, good night. Sleep tight in Tennessee. What do you mean? Why are you glad? What do you mean? I got rid of the lyrics. Baby, I'm dancing in the... How long have you been singing? Oh, thank you for supporting my singing. Oh, well, thank you. Thank you. Please keep on sharing clips with Koreans, Asians, Chinese, Taiwanese. I did learn how to sing as a child. They would be very disappointed in my singing now, though. I just popped on. Good job. Good job, John Foster. Elevation women, but sadly I only talked to a Korean lady. Beautiful and sweet. Share this with her. She'll like it. She'll like it. She'll like it. Maybe. I do dance to John Foster. Indeed, I'm quite well-rounded, very wholesome. I dance, I did theater, I do singing, all kinds of things. Does she want Taylor Swift? That type of song? I didn't even know how to sing the Johnny Cash song, but I probably did something. When I'm performing in full delight, I don't even know what I'm doing. John Foster, can you like the live? Can we get 20 likes, please? Come on. 20. Come on. I can dance right now for you. Likes, come on. Tomorrow I'm gonna dance more. 20 likes. Tomorrow I'm gonna dance more as a Valentine's Day special, which I've already started my Valentine's Day special with my Valentine right here and wearing red. Happy Valentine's Day! Where is happy Valentine's Day? Happy Valentine's Day. What do you mean? I just said I would do a special. I haven't decided what I'll do yet. What do you mean? And hetamine. Okay. We were just kids when we fell in love. She just walked away. She just walked. Not knowing what it was. $20 likes, come on. Let's go. Don't be lazy. Come on. We were just kids when we yes! Fell in love, not knowing what it was. No, 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 no. Oh, darling, just hold me tight. I forget the words quite right. She's turning on the shredder. He's really astrophysicist dances and sings. That's great. John Foster, you need to share my live with everybody you know and clip it constantly and like it constantly and come back next time tomorrow and share it and like it and share it and like it constantly. Goodbye. Slip tight. Good night. I have a life to live now. Oh, and John Foster, you can give me song recommendations and song requests for what I should sing tomorrow or next time. So, yeah. Yeah. Do that. Okay? Good night. Goodbye.